Think about the vibrant red of a ruby, or the quiet strength in a jet engine, or even the iron in your own blood, tirelessly carrying oxygen.
Yeah.
What's the surprising connection between these totally different yet super important parts of our world?
The fascinating group of elements we call transition metals.
Welcome to the Deep Dive, where we take your source material and uncover the most important insights. Today, we're plunging into Chapter 21, Transition Metals and Coordination Chemistry, from Zumdahl, and DeCoste's chemistry textbook.
Hmm.
Our mission for you today is pretty simple. We want to demystify these incredibly versatile elements and their, well, intricate compounds, make them clear, relatable, and applicable to the real world, all without needing a single diagram.
Absolutely. And hopefully you'll walk away from this deep dive not just knowing what transition metals are, but
Right.
really understanding why they behave the way they do,
Right.
how they form these incredibly intricate structures, and their really astonishing impact on everything from the technology that powers our lives, the industries building our world.
To your own body.
Exactly, right down to your own fundamental biological processes.
Okay, let's get into it. So, unlike the representative elements on the periodic table, where chemistry often shifts dramatically as you move across a row,
Right, big changes.
transition metals often show surprising similarities both horizontally and vertically. But what truly sets them apart, as I understand it, is their electron configuration. Their outermost electrons are primarily d electrons.
That's the key. These are considered inner electrons. They're a bit more tucked away, and they don't participate in bonding quite as readily as the S and P electrons you might remember from other elements.
Ah, okay.
And that unique electron setup, that's really the secret to their distinctive properties. As a class, they all act as typical metals. They're shiny, they conduct heat and electricity remarkably well.
Like copper wiring.
Exactly. Silver is technically the best conductor, but copper is a very close second, which is precisely why your home and, well, factories are likely wired with it.
Makes
Yet, they also display this huge range of physical characteristics. You've got tungsten melting at a scorching 3,400 degrees Celsius, perfect for old light bulb filaments.
Wow.
But then, mercury is a liquid at room temperature. Some, like iron and titanium, they're incredibly hard and strong, essential for structural materials. Others, like gold and silver, are relatively soft, malleable.
And their importance isn't just, academic. Governments globally really focus on minerals like lithium, nickel, cobalt, platinum,
Oh.
calling them strategic and critical.
Yeah, that's a big deal.
It's not just jargon. It signifies their vital role in everything from renewable energy tech to defense systems, and often a lot of that supply has to be imported.
And what's fascinating is when these metals form ionic compounds, they show a few characteristics that are, well, much less common with other elements.
Okay, so when they form ionic compounds, what are these unique characteristics we should be looking for?
You'll typically see four key features. First, they often display multiple oxidation states. Take iron, for example. It can form both in Fe2 plus ion, like in Fe2, and in Fe3 plus ion, in Fe3. That flexibility is a real hallmark. Makes them incredibly versatile in reactions.
Right, they can swap electrons differently. And second,
They love being at the center of things, forming what we call complex ions.
yeah,
You often find a transition metal ion right at the core, surrounded by a group of molecules or other ions.
like a central hub.
Kind of like that, yeah. A central magnet attracting smaller pieces. Third, most of these compounds are incredibly vibrant and colorful.
Not just slightly colored.
Oh no, we're talking rich reds, blues, greens, violets, really intense colors. And finally, many are paramagnetic,
Paramagnetic, meaning.
meaning they have unpaired electrons, which makes them attracted to magnetic fields.
Gotcha. Let's dive into their electron configurations a bit. Focusing on that first row, scandium to zinc, you might expect the third orbitals to fill up predictably after the fours.
Yeah, that's the simple picture.
But nature often has its quirks. Chromium, for instance, doesn't follow the expected pattern. Instead of being 4-3 predo, it actually adopts 4-3 And copper does something similar, right? It becomes 4-3 instead of 4-3.
Right. And these aren't just random glitches. They happen because the energies of the third and fourth orbitals are actually very, very similar.
Okay.
And these specific configurations, either having a half-filled 3 set like chromium or a fully filled 3 like copper, they provide a subtle but significant boost in stability. It's like nature's way of finding the lowest energy, most stable arrangement.
But here's something really crucial for you listening. In transition metal ions, the third orbitals are actually lower in energy than the 4s orbitals.
That's a key takeaway.
So when an ion forms, the 4s electrons are always lost first. For instance, a neutral manganese atom is argon 4 cis 3,3u, but if you make an Mn2 plus ion, it becomes argon 3u.
Yep, those 4s electrons go first no matter what other electrons are lost.
Okay, so how does this affect their oxidation states and reactivity?
Well, for the first few transition metals, the maximum oxidation state often comes from losing all their 4s and third electrons. Chromium, for example, can get up to +6.
Wow, losing a lot.
Yeah. But as you move further right across the period, that increasing nuclear charge pulls the third orbitals lower in energy, makes them more stable.
Harder to remove.
Exactly. It makes those third electrons harder to remove. So higher oxidation states become less common, and +2 ions become much more typical for many of these later elements.
So what does this mean for how they react, say, in solution?
Well, most of those first-row transition metals can act as pretty strong reducing agents.
Meaning they give up electrons easily.
Right. Many are even strong enough to reduce H+ ions from acid to make hydrogen gas. The big exception, though, is copper.
Ah, copper again.
Yeah, stands apart. It has that sort of noble nature, doesn't readily react with acids to produce hydrogen.
Interesting.
Now, shifting gears a bit, you'd normally expect elements to get bigger as you go down a group on the periodic table, right? More electron shells.
Yeah, that makes sense.
Surprisingly, though, the metals in the 4 and 5 base series that are in the same group, they're almost identical in size.
Wait, really? How does that work?
It's due to this thing called the lanthanide contraction.
Lanthanide contraction. Why does it contract?
It's because the 4f electrons, which fill up before the 5 beta electrons start filling, well, they're surprisingly bad at shielding the outer electrons from the increasing positive charge of the nucleus.
So the nucleus pulls harder.
Exactly. Even though there are more protons pulling, the outer electrons feel a much stronger effective pull inward than you'd expect. This leads to a smaller atomic radius than anticipated. It's like a heavier nucleus pulling those outer electrons in tighter.
And this similar size, that's important.
Hugely important. It leads to very, very similar chemistry for elements in the same group, like zirconium and hafnium. Makes them incredibly difficult to separate industrially.
Wow.
But these elements also have amazing uses. Zirconium, niobium, molybdenum, they're prized in things like space vehicle parts because they resist extremely high temperatures.
Makes sense for space.
And tantalum, which is highly resistant to body fluids, is used for things like bone replacements. Hip replacements often use tantalum.
No kidding.
Plus, the platinum group metals, ruthenium, rhodium, platinum itself, they're critical industrial catalysts. They speed up countless chemical reactions in everything from catalytic converters in cars to making pharmaceuticals.
Okay, so moving on to these coordination compounds. You said they're at the heart of this chapter.
Absolutely. So remember those complex ions we mentioned earlier?
Yeah, the metal in the middle.
Right. A coordination compound basically consists of that central transition metal ion, which acts as a Lewis acid, accepting electron pairs surrounded by a cluster of things called ligands.
Ligands. What are those?
Ligands are Lewis bases. They donate electron pairs to the metal, forming this complex ion. And then if the complex ion has a charge, you'll have counterions nearby to balance everything out.
Okay, so metal ligands, mitochondrions?
Precisely. And it was Alfred Werner, a real pioneer back in the late 19th century, who first figured this out. He talked about the metal having two kinds of valence.
Two kinds?
Yeah. What he called primary valence is what we now just call the oxidation state, the charge on the metal ion.
Okay.
And his secondary valence is what we now call the coordination number.
Coordination number, that's just how many ligands are attached.
Exactly. Simply the number of ligands directly bonded to the metal. The most common number is 6.
6 ligands? What shape does that make?
That typically arranges the ligands in an octahedral shape around the metal. Think of it like points on a diamond shape. The next most common is 4.
And that can be?
That can form either a tetrahedral shape, like a pyramid, or sometimes a flat, square, planar shape. And occasionally you'll see a coordination number of just 2, which gives you a straight linear arrangement.
Got it. So the ligands are the key partners here.
They really are. Ligands are neutral molecules or ions that have at least one lone electron pair. That's a pair of electrons not already tied up in bonding within the ligand itself.
And they donate that pair.
Yes. They donate that lone pair to the metal ion, forming a special type of bond we call a coordinate covalent bond.
Okay. Are all ligands the same?
Nope. Some ligands are called monodentate. Think mono for one, dentate like tooth, they bond to the metal at just one point.
Like water.
Exactly. Water's a great example. When it acts as a ligand, we actually call it aqua. Ammonia is another common one. We call it amine when it's a ligand.
Aquaamine.
Okay. But then you get the really interesting ones, the chelating ligands. The name comes from the Greek word for claw,
Claw. Why?
because these ligands, which we also call polydentate poly for many teeth, have multiple atoms with lone pairs. They can form several bonds to the same metal ion, literally wrapping around it like a crab's claw.
Ah, I see. That sounds stable.
It is. It creates a much more stable complex. A common example is ethylenediamine, usually shortened to N. It's bidentate two teeth, or 2 points of attachment.
Okay.
But the real superstar, the champion chelator, is EDTA. That stands for ethylene idiometatracetate.
EDTA sounds complex.
It is. It's hexadentate. You can form 6 bonds to a single metal ion. It completely surrounds it like a cage.
6 bonds from one molecule. Wow. Is that just a lab curiosity?
Oh, absolutely not. EDTA is crucial in the real world. It's used medically to scavenge toxic heavy metals like lead from the body. It's called chelation therapy.
To remove lead.
Yes, it grabs onto the lead ions and helps your body excrete them safely. You also find EDTA in countless consumer products.
Like what?
Sodas, salad dressings, bar soaps. It's added to tie up trace metal ions that would otherwise cause spoilage or weird color changes or form cloudy precipitates. It's silently working to keep your food fresh and your product stable.
Huh, I never knew that. Okay, so how do we name these complicated things?
Nomenclature. Yes, there's a very precise chemical language for naming these coordination compounds. It ensures every detail of their structure and charge is crystal clear.
Rules, I bet.
Lots of rules. You name the cligans first, then the anion. Within the complex ion itself, you name the ligands first, alphabetically, before the metal. Anionic ligands get an O suffix, like chloro for clo. Neutral ligands mostly use their molecule names, but there are those special ones like aqua and amine, plus carbonyl for CO and nitrosyl for NO.
Okay, ligands first, alphabetically.
Then prefixes like di, tri, tetra tell you how many of each simple ligand there are. If the ligand name itself is complicated or already has a prefix, you use bis, tris, tetrachus instead.
Bis, tris.
Okay, after all the ligands, you name the metal. Its oxidation state is given in Roman numerals in parentheses right after the metal name. And one more twist. If the entire complex ion is negatively charged, the metal name gets an et suffix, like ferrate for iron or cumperate for copper.
Whoa, okay, that's a lot. Can we try an example? Like, coen, euro.
Good one. Okay, ligands first. 5 NH-amine and 1 chloro. Alphabetically, amine comes before chloro, so pentaminochloro. The metal is cobalt. We need its oxidation state. Let's see, ammonia is neutral, chloride is -1. There are 2 chloride counterions, so that's -2 total outside. The complex ion must be +2 to balance. If the complex is +2 and the chloroligand is -1, the cobalt must be +3.
Right, plus
So pentaminochlorocobalt, then the counterion chloride. So pentaminochlorocobalt chloride.
Pentaminochlorocobalt with chloride. Okay, it's like building a sentence.
Exactly. It seems complex, but it's systematic. How about Kefian-Urey?
Okay, K is potassium. That's the cation. The complex ion is FCN-ur. Ligand is CNU, cyano. 6 of them, so hexacyano. Metal is iron, Me. Since the complex is negative, iron becomes ferrate, oxidation state. Cyanide is many of 1. 6 of them makes -6 total. The complex is many 3 overall, so the iron must be +3.
Perfect. So putting it together,
Potassium hexacyanoferrate.
you got it. It's vital for scientists worldwide to communicate precisely about these molecules. Think about drug development or industrial processes. A tiny mistake in naming could be dangerous. So while the rules are intricate, the system provides a universal, unambiguous way to describe these structures.
Okay, that makes sense. Now let's talk about something else that sounds complicated. Isomers.
Ah, yes, isomers. This is where things get really interesting structurally. Sometimes 2 compounds can have the exact same chemical formula, same number and type of atoms, but totally different properties.
2 atoms, different properties. How?
Because the atoms are arranged differently. They're isomers. We group them into 2 main types.
We sure?
Structural isomers, where the actual connections, the bonds between atoms are different, and stereoisomers, where all the bonds are the same, but the arrangement of atoms in 3D space is different.
Okay, structural first. What kinds are there?
One type is coordination isomerism. Here, the composition of the complex ion itself changes. For example, you could have Kr NH aereo. Here, sulfate is a ligand, bromide is the counterion.
Right.
Its coordination isomer would be Cr and A aero SO. Now, bromide is the ligand, and sulfate is the caterion. Same atoms overall, but different complex ion.
They swapped places.
Exactly. Another type is linkage isomerism. This happens when a ligand can attach to the metal through different atoms within the ligand itself.
Like the thiocyanate ion, SCM.
Perfect example. It can bond through the sulfur atom or through the nitrogen atom. The nitrate ion, NO, is another one. It can bond via the nitrogen or one of the oxygens. This small change can even affect the color. A cobalt complex with NOO bonded through nitrogen might be yellow. We call it the nitro complex. But if it bonds through oxygen, it might be red, the nitrito complex.
Wow, just flipping the connection changes the color. Okay, what about the other main type? Stereoisomers.
Right, stereoisomers. Same bonds, different spatial arrangement. The first kind here is geometrical isomerism, often called cis-trans isomerism.
Cis-trans, I've heard that.
It occurs when ligands can be either next to each other, that's cis, or across from each other, that's trans. Think about a square planar complex, like PTNH or...
Platinum with 2 ammonias and 2 chlorides.
Exactly. In the cis isomer, the 2 ammonias and the 2 chlorides are adjacent, side by side at 90 degrees. In the trans isomer, the 2 ammonias are opposite each other, 180 degrees apart.
Okay, adjacent versus opposite. This doesn't matter.
Does it ever? Here's where it gets really amazing. Cis-PTNHO, which is commonly known as cisplatin.
Cisplatin, yeah, the cancer drug.
Right. It's a powerful anti-tumor agent, very effective against certain cancers that resist other treatments. But it's trans isomer, the one where the ammonias are opposite.
Yeah.
It has no anti-cancer effect whatsoever.
Whoa, just changing the arrangement from adjacent to opposite turns off the biological activity.
Completely. It starkly highlights how critical specific molecular geometry is in biological systems. A tiny difference in 3D shape can literally be the difference between an effective medicine and something useless.
That's incredible. Okay, what's the second type of stereoisomerism?
The second type is optical isomerism, also known as chirality.
Chirality, like hands.
Exactly like your hands. These isomers have opposite effects on something called plane polarized light. They're chiral, which means they are non-superimposable mirror images of each other.
Like my left hand and my right hand. I can't perfectly overlay them.
Precisely. You can't rotate your right hand in any way to make it perfectly match your left. Molecules can be like that too. These non-superimposable mirror image molecules are called enantiomers.
Enantiomers, okay. And they affect polarized light differently.
Yes, one enantiomer will rotate the plane of polarized light to the right. We call that dextrorotatory, or D. And its mirror image will rotate it an equal amount to the left, levorotatory, or EEL.
What's the real-world impact of this chirality?
It's huge, especially in biology. Most important biomolecules in your body, proteins, DNA, sugars, are chiral. They exist predominantly as one specific enantiomer.
Only one-handedness.
Mostly, yes. And just like your right hand needs another right hand for a proper handshake, a chiral receptor site in your body often needs the correctly shaped chiral isomer of a drug molecule to bind effectively.
Ah, so the wrong hand might not fit the receptor.
Exactly. This makes drug synthesis incredibly complex and challenging. Often, only one enantiomer of a drug is biologically active and beneficial. The other enantiomer might be inactive, or sometimes, unfortunately, even harmful. Getting just the right hand is critical.
That makes sense. Okay, so we've talked structure and bonding, but what about those key properties you mentioned earlier, color and magnetism?
Right. While simpler models like Lewis structures help us visualize bonding, they don't really explain why these complex ions have such vibrant colors or why they behave differently in magnetic fields. For that, we need a different model.
And that model is?
The crystal field model. It takes a different approach. It focuses purely on how the negatively charged ligands affect the energies of the metal ions' d orbitals.
So it's about the ligands interacting with the metal's d electrons.
Essentially, yes. Imagine the ligands as tiny negative point charges surrounding the central metal ion. These negative points will repel the electrons that are already in the metal's d orbitals.
Okay, repulsion. How does that affect the orbitals?
Let's picture an octahedral complex again, where ligands sit along the x, y, and z axes. Now, the d orbitals themselves have specific shapes and orientations. Some of them, specifically the dxc, xy orbitals, have lobes that point directly at these incoming negative ligands.
So electrons in those orbitals get pushed away more.
Exactly. They experience greater repulsion, which raises their energy level. The other three d orbitals, the DXE have lobes that point between the axes between the ligands.
Less repulsion there.
Right. Electrons in those orbitals experience less repulsion, so they end up being lower in energy compared to where they started.
So the 5d orbitals, which were all the same energy in a free metal ion, they split.
They split into two distinct energy levels in an octahedral field. You get a lower energy set of 3 orbitals, we call this the T set, and a higher energy set of 2 orbitals, the egg set.
T and egg. Okay.
And the energy difference between these two sets is incredibly important. We call it delta, often written as A, or sometimes A for octahedral.
And this splitting, this G, explains magnetism.
Precisely. It depends on the size of that energy gap compared to the energy it costs to pair up electrons in the same orbital. If A is very large, which happens with what we call strong field ligands, it's energetically easier for electrons to pair up in the lower t orbitals before occupying the higher egg orbitals.
So they fill the bottom level first, even pairing up.
Yes. This creates what we call low-spin complexes. They often end up being diamagnetic because all the electrons are paired.
Okay. What if it's small?
If A is small, which happens with weak field ligands, the energy cost of pairing electrons is greater than the energy needed to jump the gap. So electrons will spread out and occupy all 5 orbitals singly, following Hund's rule, before they start pairing up.
They spread out first.
Right. This leads to high-spin complexes, which are often paramagnetic because they have unpaired electrons. We can actually rank ligands based on their ability to cause this splitting. It's called the spectrochemical series. Cyanide ion, CNF, for example, is a strong field ligand, causing large splitting. Fluoride ion, FRO, is a weak field ligand, causing small splitting.
And the metal matters, too.
Yes. Generally, a higher charge on the metal ion leads to a larger splitting, a bigger O.
Okay, that explains magnetism. What about the colors?
The vibrant colors come directly from that same d orbital splitting, that energy gap.
Oh.
When white light, which contains all colors, shines on a complex ion solution,
Yeah.
the complex absorbs a specific wavelength, a specific color of light. The energy of that absorbed light photon corresponds exactly to the energy gap.
So it absorbs the energy needed to jump an electron.
Exactly. It absorbs the energy needed to promote an electron from a lower t orbital to a higher egg orbital. The color you actually see in the solution is the complementary color to the one that was absorbed.
Complementary color? Like on a color wheel.
Precisely. So if a complex absorbs yellow-green light, like that TH complex we mentioned.
Titanium with water ligands?
Right. It absorbs in the yellow-green region. What's left? The light your eye perceives is the complementary color, which is violet.
So the color we see is the light not absorbed.
Exactly. And what's truly fascinating is how this plays out in the natural world.
Like with gemstones.
Absolutely. The stunning colors of gems like rubies, red, sapphires, blue, and emeralds, green, all come from trace amounts of transition metal ions, often chromium or iron, substituting into the crystal lattice of an otherwise colorless mineral, like aluminum oxide for rubies and sapphires.
So tiny bits of metal cause the color.
Yes. These impurity ions create specific d orbital splittings within the crystal structure. They absorb certain colors of incoming light and transmit the others, giving the gem its characteristic color. Alexandrite is an amazing example. It changes color.
Changes color how?
It looks reddish in incandescent light, like firelight or an old light bulb, but bluish-green in daylight or fluorescent light. It's because the cryons in it absorb light differently depending on the light source's spectrum, all due to that crystal field splitting.
That's wild. Does this model work for other shapes besides octahedral?
It does. The principles are the same, but the splitting patterns differ. In tetrahedral complexes, for instance, the ligands approach from different angles. So the orbital splitting pattern is actually reversed compared to octahedral.
Reversed?
Yeah, the set of 3 orbitals is higher in energy and the set of 2 is lower. Also, the overall splitting energy for tetrahedral is much smaller, only about 4/9 of the octahedral splitting for the same metal and ligands.
Much smaller gap.
Much smaller. This means beat is almost always smaller than the pairing energy. So tetrahedral complexes are essentially always high spin. Electrons spread out before pairing. Square planar and linear complexes also have their own distinct, unique splitting patterns, all based on how the ligands interact electrostatically with the 2 orbitals.
Okay, this crystal field theory really ties color and magnetism together. Now let's shift to the biological side. You mentioned transition metals are crucial there.
Oh, absolutely. Biological superstars. Their ability to easily coordinate with ligands, hold on to them, let them go, and also to change oxidation states, gain or lose electrons, makes them perfectly suited for the dynamic processes of life.
Which ones are important?
Many of the first-row transition metals are essential for human health. Chromium is involved in blood sugar regulation. Zinc is found in over 150 different biomolecules, doing all sorts of jobs. Copper and iron are absolutely critical for respiration, how we use oxygen.
Iron seems particularly important.
Iron is central, really, in almost all living cells. In us mammals, it's the key player in oxygen transport and storage. You find it in cytochromes, which are electron transfer molecules vital for the respiratory chain where we generate energy.
Okay.
These cytochromes contain an iron complex called heme. It's an iol, or Phe ion, sitting in the middle of a flat organic ring structure called a porphyrin.
Heme. Sounds familiar.
It should. And interestingly, chlorophyll, the molecule that captures sunlight for photosynthesis in plants, is a very similar structure, but with a magnesium ion in the center of the porphyrin ring instead of iron. Nature reuses good designs.
Wow. So heme is in more than just cytochromes.
Oh yes. It's also the core of myoglobin, which stores oxygen in our muscles, and hemoglobin, which transports oxygen in our blood.
Hemoglobin, right, in red blood cells.
Exactly. Both use that heme complex. In myoglobin, the Phe ion is bound to 4 nitrogen atoms from the porphyrin ring, 1 nitrogen from a nearby protein chain, leaving 1 coordination site open.
For oxygen.
Precisely, for an oro molecule to bind. And the protein part wrapped around the heme is incredibly important. It acts like a protective pocket.
Why does it need protection?
Because free-heating water would react with oxygen in a way that oxidizes the Phe to Phe, which cannot bind oxygen anymore. The protein prevents this, partly by blocking 2 heme groups from getting close enough for oxygen to form a bridge between them, which is the pathway to that unwanted oxidation. It keeps the iron in the functional +2 state.
Clever design.
Yeah.
And hemoglobin.
Hemoglobin is even more complex. It's essentially 4 myoglobin-like units packed together. So 1 hemoglobin molecule can bind and transport 4 Ouros molecules.
4 times the capacity.
Right. And when hemoglobin binds oxygen, it forms oxyhemoglobin, which is bright red. Oxygen acts as a strong field ligand here, causing the Phe electrons to pair up, making it diamagnetic. When it releases oxygen, say in the tissues, a water molecule takes oxygen's place. Water is a weak field ligand, so the complex becomes deoxyhemoglobin, which is bluish and paramagnetic because the electrons remain unpaired.
And that's why venous blood looks bluish through the skin.
That color difference contributes to it, yes. It really shows the link between ligand type, electron spin state, and observable properties.
And it also shows how sensitive biology is to structure. You mentioned sickle cell disease.
A tragic example. A single tiny error changing just 1 amino acid in the long protein chain of hemoglobin drastically alters the molecule's shape, especially the deoxyhemoglobin form.
What happened?
These altered hemoglobin molecules clump together inside red blood cells when oxygen levels are low, forcing the cells into a distorted, rigid sickle shape. These sickled cells can't squeeze through tiny capillaries, causing blockages, pain, organ damage, a devastating illustration of structure dictating function.
Wow. That same structure-function link must explain other things too, like high-altitude sickness.
Exactly. At high altitudes, the partial pressure of oxygen is lower. The equilibrium for oxygen binding to hemoglobin shifts. Less oxygen gets bound, leading to symptoms like fatigue and dizziness.
Until you adapt.
Right. Your body adapts over time by producing more hemoglobin molecules to compensate. That's high-altitude acclimatization. It also explains why some gases are so toxic.
Like carbon monoxide.
Yes, CO. Carbon monoxide binds to the same Phe site in hemoglobin as oxygen does, but about 200 times more strongly.
200 times.
Yeah. It forms a stable complex called carboxyhemoglobin, effectively blocking oxygen transport and leading to asphyxiation. Cyanide ion, CNA, is another deadly poison because it binds very strongly to the iron in cytochrome oxidase, a crucial enzyme at the end of the respiratory electron transport chain, shutting down cellular energy production almost instantly.
So these coordination chemistry principles are literally life and death.
Okay.
Shifting from biology to industry. Iron isn't just vital in our bodies, it's fundamental to civilization. How do we get it from the ground and turn it into steel?
That whole process falls under the banner of metallurgy.
Metal.
It's the science and technology of extracting metals from their natural sources, called ores, and preparing them for practical use. Ores are typically mixtures of valuable minerals containing the metal, mixed with unwanted rock and sand called gangue.
So how do you get the metal out?
It usually involves several steps. Mining the ore, some kind of pretreatment to concentrate the desired mineral, then chemically reducing the metal compound, often an oxide, to the free metal, followed by purification, refining, and often mixing it with other elements to form an alloy with specific properties.
Okay, pretreatment and reduction.
After mining and crushing the ore, concentration often uses physical methods like flotation, where the mineral particles are made to stick to oily bubbles and float away from the gangue. If the mineral isn't already an oxide, it's often roasted, heated strongly in air to convert it into the metal oxide.
Why oxide?
Because oxides are generally easier to reduce to the free metal, the reduction step itself is often done at high temperatures, a process called smelting. For iron oxide, the main reducing agent in a blast furnace is carbon monoxide, COO.
Is high temperature the only way?
Not always. There's also hydrometallurgy, which uses aqueous solutions water-based chemistry to extract metals. This is often better for low-grade ores and can be more environmentally friendly than high-temperature pyrometallurgy. It often involves leaching, dissolving the metal out of the ore, frequently by forming soluble complex ions.
Complex ions again, like with gold.
Exactly. The cyanidation process for recovering gold from low-grade ores is a classic example. Crushed ore is treated with cyanide solution and air. The gold gets oxidized and forms a soluble complex ion, which can then be separated and the gold recovered.
Fascinating. But back to iron and steel. The main method is the blast furnace.
Still the dominant method for primary iron production, yes. It's a massive continuous reactor. You feed iron ore, like hematite, fatto of coke, which is basically carbon, and limestone into the top. Hot air is blasted in near the bottom.
What does everything do?
The hot air burns some of the coke to produce heat and carbon monoxide, CO. This CO is the primary reducing agent, reacting with the iron oxides in stages as the materials descend, ultimately producing molten iron. The limestone acts as a flux, decomposes in the heat to calcium oxide, CaO, which reacts with silicon dioxide, silica, and other acidic impurities from the ore to form a molten mixture called slag.
Slag. That's the waste.
Essentially, it's mostly calcium silicate. Because it's less dense than molten iron, it floats on top, allowing the molten iron and slag to be tapped off separately from the bottom of the furnace. The iron produced here is called pig iron.
Pig iron, is that usable?
Not really directly. It's quite impure, maybe 90–95% iron, but with around 4–5% carbon dissolved in it, plus silicon, manganese, phosphorus. It's very brittle. To make steel, you need to remove most of these impurities, especially the excess carbon.
How do you do that?
Through an oxidation process, the molten pig iron is transferred to another furnace, like a basic oxygen furnace, and high-purity oxygen is blown through it or over it.
Oxygen burns off the impurities.
Precisely. The excess carbon reacts to form CO and co-uro gases. Silicon, manganese, and phosphorus oxides are formed and react with added fluxes, like calcium oxide, to form more slag, which is removed. By carefully controlling the process, you can reduce the carbon content to the desired level for steel, typically less than 1.5%.
And that gives you steel. But aren't there different kinds of steel?
Absolutely. The properties of steel can be further fine-tuned by adding other alloying elements like chromium, nickel, vanadium for stainless or high-strength steels, and by heat treatment.
Heat treatment, like heating and cooling.
Exactly. The way steel is heated and cooled affects its microstructure, particularly the formation and distribution of a very hard iron carbide compound called cementite. Rapid cooling, quenching, can make steel very hard but brittle. Slower cooling, or reheating to moderate temperatures, tempering, allows the microstructure to rearrange, achieving different balances of hardness, strength, and ductility. This allows us to tailor steel for incredibly diverse applications, from flexible springs to rigid structural beams to razor-sharp surgical instruments.
Amazing how much chemistry goes into making something seemingly simple like steel. Okay, let's try to wrap this up.
It's been quite a journey.
Yeah. So we started with the unique electron configurations of transition metals, those d electrons, giving them their versatility. Then we dove into the intricate dance between metals and ligands in coordination complexes.
And the fascinating world of isomerism, where just arranging the same atoms differently, like with cisplatin, can have huge consequences.
Right. Then the crystal field model gave us a way to understand their vibrant colors and magnetic behavior, linking back to those d orbital energies.
And finally, we saw their absolutely vital roles in both biology, think hemoglobin carrying oxygen, and heavy industry, like the production of iron and steel that builds our world.
Phew, we really covered a lot today.
Hopefully you listening now have a deeper appreciation for how these elements, often kind of hidden within these complex structures, really govern so much around us. From the colors we see in gemstones to the air we breathe and the bridges and buildings we rely on.
And maybe a provocative thought to leave you with. Consider how, despite this incredible diversity in properties and applications, the core principles, electron configuration, orbital interactions, Lewis acid-base chemistry, really unify our understanding of all these different phenomena.
It makes you wonder what other hidden connections might be unveiled if we keep diving deeper into the fundamental properties of matter.
Keep exploring, keep questioning, and keep making those incredible connections. Thank you so much for joining us on this deep dive into transition metals and coordination chemistry.
We hope you're feeling a little more well-informed.